I wanted to just touch bases on, so what we're doing today is we're going to be covering the second and third lecture from Chapter 8. I'm probably going to go pretty light on the second lecture because it's more of a conceptual component than it is related to the problems that you're going to be working. And then we'll go ahead and move on into the third lecture and kind of focus in on the types of problems that you're going to be working. Next Tuesday is a scheduled project review and work day, so I will be on campus. And so for those of you who haven't completed your projects, it's going to be an opportunity for you to meet with me during class time or schedule something outside of class time. Again, I think there's a couple of the groups that probably need to take advantage of that. We'll come back then the Tuesday after Thanksgiving will be our project presentation. So you need to be prepared to present to the class where you're at with your project at that point, right? And then they're going to give you feedback on what you're going to share with your client. And then from that point on, then we'll need to set up individual presentation times. So your group will need to go with HR. Your group will need to set up a time with what works for you, me, and the university bookstore. And Hunter, I'm sure we can just sit down with your group and go through that. So, Scotty?
For the class presentations, are we supposed to, dress nicely?
I'm not as concerned about that when you do present to your clients. Okay. I have an expectation that you'll be in at least business casual. So you don't have to have suits and ties, but at least nice slacks and shirts. Okay? And then during finals week, we'll just have the exam over Chapter 8. So that's what we'll be covering during finals week. Okay? So what you'll notice then is you'll have B and C homework that comes from today's lecture, and then you'll have, if I can get across to the other screen here, then you'll have your in-class presentations aren't worth quite as much. They're worth 28 points, and your client presentations are worth 100 points. The in-class is your opportunity to practice and run through, because I want you to be polished for when you present to your client. And then, again, you'll get feedback from me and other students as well in terms of how that presentation goes. Okay? So any questions about kind of where we're headed for the rest of the semester? Okay. So for those that have finished A, B, and C, you're kind of on the wind down. You're just focused on the presentation. For the rest of you, you're going to have kind of a crunch time, or not, depending on if you decide to complete or not complete. So that's where we're at in terms of schedule. All right. And again, in order to kind of keep things moving, I'm going to go ahead and head into the part 2 of managing flow variability and safety capacity. And so we talked about this last Thursday, and we just got a little bit of a taste for it. And we're using some similar measures that we've used in the past, right? So we've got in the past we've said that R is equal to the throughput, okay? And so in the examples that we're using, right, the throughput that we're going to take is either the minimum of either the arrival rate of our customers or the customers per time, or the rate that we can process, right? And so R sub I is what we call the inflow rate, R sub P is the service rate, right? And so the R is consistent with throughput, so we're always talking about customers per time when we're talking about the R, okay? And so I think that's going to be helpful as you try to organize your thoughts about about how these measures interplay. So R sub P being the service rate is our process capacity, okay? So it's the maximum rate at which customers can be processed by all the servers in the server pool. R sub I is our inflow rate, right? And it's customers per time, all right? And let's take a look at example 8.1. See what it tells us here. So example 8.1 has us talking about the Vancouver International Airport security checkpoint, right? And so it's one that we kind of took a quick look at last Thursday. Each passenger places his or her carry-on luggage on a moving belt to be scanned by an X-ray machine. So each passenger is a customer. And the X-ray machine is considered the server, which processes customers in the first-come, first-served order. Okay? So suppose as before, customers carry on average 1.5 bags, and the X-ray machine can scan 18 bags per minute. So the X-ray machine can screen up to 12 passengers' bags per minute. And the average time to process a passenger then is 1 over 12 minutes, right? Because that's when we talk about time to process, all right? So the customer carries average of 1.5 bags. So again, to get to our X-ray can scan 18 bags per minute. We take 18 bags times one person for 1.5 bags, and that gets us to the 12 people per minute. So that's how we're transitioning, right, into that measurement of 12 people per minute. So 12 people per minute is going to be the time to process, or excuse me, it's going to be the processing rate, right? And so to get to, because it's people per minute, so that's that rate. To get to the time to process, we take the inverse, which is then how many minutes per person, okay? And so 1 over 12 minutes says that we can do 1 every 5 seconds. So and at peak arrival rate, we have an inflow rate of 15 customers per minute. Therefore, our average inter-arrival time, right, we're taking the inverse to get to the time, is 1 customer over 15 minutes or every 4 seconds, okay? And so our passenger throughput is going to be the minimum of the inflow rate or the processing rate. So we have 15 or 12, so we have 12 people per minute. All right, so visually, this is where I'm just going to use these. They go into a lot of depth in the middle of this chapter to try to make this point. And so, but visually what you see is that it takes us longer to process than it does in terms of, we have more people arriving than as fast as we can process. So what happens is we just continue to get an increasing queue because we're not able to process people. So this is not a stable process, right? We have more people to process than what we're able to accommodate, okay? Right? And so if we continue that example, if we reschedule the flight, so now that our arrival rate is 10 customers per minute, so then our inter-arrival rate is 1 customer every 10 minutes or every 6 seconds, right? Then, and our processing rate is still 12 per minute, okay? Then we say that our passenger throughput now is either the minimum of our inflow rate or our processing rate, so our passenger throughput is now 10, okay? And if we want to think about what our safety capacity is, it's the difference between how fast we can process less how many customers we have arriving, right? So we've got 12 minus 10 gives us 2 people per minute for safety capacity. Capacity utilization then is our inflow rate divided by our processing rate, okay? So if I have 10 customers arriving divided by 12, that gives us an 83.3% capacity utilization. Okay, so those just might take you a little time to get comfortable with the terms, but you just spend a little bit of time with that, and as you work through the problems, I think people, did I hear a question?
Is that good? Like, is that what you're shooting for as a point, like 8 something, or are you looking for closer to 100?
So it depends, right? So
yeah.
the question is, what are you competing on? So if you're competing on cost, you can have, so what happens if you go into a bank and all the tellers are busy? Are you going to wait a short amount of time? So they have lots of tellers, but they're all busy. Are you going to wait a shorter amount of time or a longer amount of time if they're busy?
Longer.
Longer, right? And so that's, their utilization is high, so you're going to wait longer. So it's really not so much about is that good or bad, it's what are you targeting, right? Are you, if you're competing on cost, like Walmart, people will wait in line because they're there for low cost, right? If you're competing on quality, like maybe more of a Kroger, right? You're not as apt to want to wait in line there because you're thinking, I'm paying a little bit more for my groceries, I should get a little better service here, right? So it's not a good or bad question, it's a what are you targeting, okay? So then they show us the example, in the perfect world, right? We have customers arriving and we're able to process them. So we have nobody waiting, right? Because we get a customer in, we process, we get a customer in, we process, we get a customer in, and we process, okay? So visually that looks good, but the reality of it is, right? So if the inter-arrival and processing times are constant, queues will develop if and only if the arrival rate is greater than the processing rate. So if we have no variability in those measures, right, we should never have anybody waiting. But the reality of it is we do have that. Okay? So the long-run stability of a service process requires that on average the processing rate has to be sufficiently high to process all the arrivals. And that's what we call the stability condition, right? So if you don't have enough capacity to to handle your customers, you basically have an unstable process, and what we're trying to do is not going to help that. So, so that's, again, known as a stability condition, and it's necessary for limiting both delays and queues that will grow without limit. So we have some measures that we now kind of break apart into two components, okay? So we can talk about inventory in terms of inventory in the whole process, or we can talk about inventory in terms of inventory within the inflow part of it and inventory that are being processed. So let's use our bank example. Inventory in the inflow process would be people that are waiting in line but aren't being served, right? Inventory in the processing space is going to be those people that are actually being served, okay? And so again, inventory can be broken into two components, as can the time, right? So it's the time that you're waiting to be served, and it's the time that it takes you to be served, okay? And so we're just kind of breaking down our Little's Law into these two components. So again, total inventory is still equal to total throughput times slow time, right? Our utilization is equal to the I sub P, right, which is the inventory in processing divided by the number of servers. And our utilization then is going to be the throughput of the process divided by the throughput of the processing time. Okay? All right. So in the absence of variability, we can eliminate any waiting by ensuring that the processing rate exceeds the arrival rate. So as long as we have no variability, we just have to make sure that we can process customers faster than they arrive. Pretty common sense. However, in the real world, we have unpredictable or random variability that a service process experiences, and we call that stochastic variability. So if you hear somebody say the word stochastic, what they mean is random variability, right? That's the equivalent of stochastic. So what happens when we address or we add stochastic variability to our example from the Vancouver International Airport? Okay. Well, if we start to add in that variability, see, everybody doesn't arrive at the same time, and we're not processing them at exactly the same time, we start to get queues that are going to build up over time because of that variability that's introduced into the process. Okay? So note that while passengers 1, 2, and 3, and 5 don't have to wait, all the others do, because as time continues, that variability continues to stack on itself. So you have this bigger, the longer your process runs, the larger the issue becomes when you haven't addressed the variability. Okay? So the above example illustrates that second reason for delays and queues in a service process. Even under the stability condition that the average process rate is greater than the average arrival rate, variability in arrival processing times can lead to customer delays. Okay? So when we talk about the variability, we're just saying some customers can have short inter-arrival times, meaning that you never know, like if you anybody here worked at a bank? So my assumption is that there are certain times of the day that you don't have that many customers walking in the door. But then when you hit other times, right, you're having customers come in very regularly, right? So that's what we were just talking about. There's a variability in how often people arrive, and then there's variability in how long it takes to process each of those people. So we have these two components of variability that we address when we talk about service processes. Okay? Or let's use the example of the convenience store. What are the busy times at the convenience store?
7 to 9 a.m., 11 to 1, and 4 to 6.
So you've got these pockets where people are arriving, and I'm guessing then maybe at 2 o'clock in the morning or 3 o'clock in the morning, it's really not that busy. Yeah. So again, you've got those pockets of how long it takes people to arrive, and then what are they bringing up? Do they have one thing, or do they have 5 things, or did what they pick up doesn't have a price tag on it? So again, every time you process someone, it can take a little bit different time. Okay? So when queues build up because the variability in processing time is independent of the variability of inter-arrival times. So it doesn't mean just because customers arrive farther apart that it's going to take less time to process them or more time. Those two things, those two pieces of variability are independent of each other. You could have a lot of people arriving at the same time, and their processing times could be larger. So again, you have to come up with a way to address that. Okay, so it says, suppose in our Vancouver International Airport example, we're able to synchronize our short inter-arrival times of customers with short processing times, as well as our long inter-arrival times with longer processing times. Okay, so then it looks pretty, right? Then again, it takes me a while to process, but you know what? I've got a longer time in between, okay? But again, the reality of it is there are some things that you can do to address that, but generally speaking, right, those pieces of variability are harder to manage. So often we cannot interchange processing times across customer arrivals over time and get that synchronization, okay? So in 8.8, we start to study strategies for achieving some degree of synchronization, okay? So up to this point, what I want you to take away from this section of the chapter is that if inter-arrival times, meaning how long between your customers' arrivals, are constant, queues are only going to build up if your arrival rate is greater than your processing rate, okay? If we have unsynchronized variability in inter-arrival and or processing times, queues are going to build up even if our processing time is less than the average processing rate. Because again, we're dealing with averages rather than specifics, okay? And if variability in inter-arrival and processing times can be synchronized or correlated, queues and waiting times will be reduced, okay? So we want to take a look at what causes delays in queues, okay? So what causes the delays in queues, again, is if our servers are highly utilized, right? If my servers are extremely busy, so think about going into a restaurant and they're really busy, you're going to have to wait a little bit longer, okay? Or if I have a lot of people arriving at one time and a low processing rate, that's going to address that's going to increase the amount of time people have to wait, okay? If my variability is completely unsynchronized between my inter-arrival times and my processing times, okay? So if you haven't gotten the message at this point, variability matters, okay? And so you're trying to figure out how can we take variability out of the process. So the two key drivers of process performance are capacity utilization and stochastic variability, okay? So, and they're determined by two factors. What's the average inter-arrival time and what's the average mean and variability of processing times, okay? And the reason that we say we should measure this variability in time relative to its mean is because if my average processing time is 2 minutes, but the standard deviation is 1 minute, that means things are really not very stable, right? That's a 50%, my standard deviation is 50% of my mean, okay? On the other hand, if I have a 10-minute processing time and my standard deviation is 1 minute, that's 10% of that, right? So it's very different in terms of that variation matters, again, the message of this portion of the chapter, and so we have to measure that in relationship to the mean and the standard deviation, okay? So, and this is the part that I looked through your homework, and I don't think I've got you calculating any of this manually. If you do, there is a spreadsheet that's out there to do this manually too. But we have a formula that we can use to calculate waiting time, okay? And we have to use, in that formula, we have to use a coefficient of variation for inter-arrival times, meaning that we're comparing our mean and our standard deviation for inter-arrival times, a coefficient of variation for processing times. So we're using in that coefficient, again, it's the ratio of the standard deviation to the mean, okay? And these measures are used to calculate the queue length. So here's our pretty queue length formula, right? And we've said that utilization matters, right, in terms of how long people have to wait. So the higher the utilization, the longer people have to wait. And the variability matters. The more highly variable our process is, the more people are going to have to wait, okay? So the length of time that people are, or the number of people that are going to be in inventory, or the length of our line is going to be related to that utilization and those coefficients of inter-arrival times and coefficients of processing times, okay? So to break it down, utilization is equal to the inflow rate divided by the processing rate, where the processing rate is equal to the number of servers. This is a new variable for you. C is the number of servers divided by the average processing time. Basically what you're saying is that if I have one server and it takes me 10 minutes, right, then that's my processing rate. But if I have 2 servers and it takes me 10 minutes, I need to adjust my processing rate because I can handle 2 customers at a time. The coefficient of the inter-arrival rate and the coefficient of the processing rate are those coefficients of variation, okay? And we're going to assume that they're independent of each other. And basically, this is just a visual that shows as utilization increases and variability increases, our waiting times are going to go up. Okay, that's just a visual showing that. All right, I'm going to go ahead and switch over to Excel because this, I've got the example here. So basically, we're given this inter-arrival times. This is example 841, okay? And in 8.4 it says that we observed the inter-arrival time of 10 passengers. So you can see I have my 10 passengers listed there, and then I've got their 10 arrival time in seconds, okay? So if you notice, we're dealing with this both in terms of the 2 components of our variability, right? Here I've got the arrival time variability, and here I've got the processing time variability. Okay? She says as she corrects that to processing time. So that being said, I can find the average inter-arrival time, right? And one of the keys here is, like, I've had students read this out of the book and understand that there are 10 passengers, and so they want to sum up the times that they have and divide them by 10. But the fact of the matter is passenger 1 has no inter-arrival time. That's when the process begins. So you're actually then going to be dividing it by 9. Okay? And then to get my inflow rate, right, I take the inverse of my inter-arrival time to get my customers per time. Right? And then I use Excel to get my standard deviation, okay? And then I can plug and play into the formula that we've got to get my coefficient of inter-arrival time. And so I'm taking the standard deviation divided by the average inter-arrival time, okay? And I'm just, again, I'm not going to spend a lot of time on this because I think we need to spend the majority of our time today on the actual types of problems you're going to be working. But this is one method of calculating how long your customers are going to have to wait. And without the Performance XLS spreadsheet that we're going to use today, right, this is the approach that you have to take. And it only works, it's only stable for when you have 1 server. Okay, so we've got some challenges with this approach. But we can, again, I'm going to calculate my average processing time. I'm going to then calculate the inverse of that. It gives me my processing rate. Right? I can calculate my standard deviation given that data using Excel. Then I can get my coefficient of processing, right? And then I can plug and play that into this formula, right? So I can get my utilization, I can get my coefficient of inflow, and I can get my coefficient of processing and finish that out, okay? So it's just one approach, and it's not, in my opinion, it works when you just have basic information and you've got 1 server, but it's not as effective when we have some other challenges introduced. So let's go ahead and talk about what those challenges might be. And I did take a quick look. I don't think this is one of your homework problems, so again, I'm going to go ahead and move on to some things that we will need to look at. All right? So that's kind of that second section. Let's go ahead and move on to part 3. So in part 3, we're going to deal with something that's called the exponential model. And the exponential model deals with what's called Poisson arrivals. Okay? And I'll have to tell you, when I first started teaching this class, I had to go back and refresh on what that means. Basically, it means that you have this infinite pool of potential arrivals who arrive completely randomly and independently of one another at an average rate that's constant over time. Okay, so it's basically you can get the average rate. But the fact of the matter is, if I were looking at all of you, Rachel could walk in, right on the mean, right? Courtney could come in 2 minutes after the mean. Zach could come in right after Courtney. So every single one of you is independent of what's happened previously. And that's what the exponential model really does a good job of addressing. Okay? So when we talk about exponential processing time, again, just like the arrival time, it's completely unpredictable. Just because Rachel takes so long to process doesn't mean that Courtney's going to, there's no relationship. It's completely independent of each other. So it's completely random and unpredictable, which means then during the process, the time remaining does not depend on the time elapsed, okay? But it has a mean time of T sub P, okay? So when we start to say, well, what does that mean to us, right? We're saying then in this calculation that our coefficients that we calculated in the previous formula are going to be at 1, okay? And so again, recognize that this is a coefficient of the inner arrival time, and this is the coefficient of the processing time. In the exponential model, we set the standard deviation to it does a calculation to adjust to make the standard deviation be 1. Okay? So if our server, little c represents the number of servers, is 1, and our time then is 1 over, right, the processing rate minus the inflow rate, then we can restate that to say that our inventory then is equal to our inflow rate times our time. Okay? If c is greater than or equal to 2, right, meaning that we have more than one server, we can no longer use our formula. Okay? And so we have to use the performance.xls spreadsheet. Okay? All right. Let me go ahead and open up these Chapter 8 examples. So what I want to show you is this is the copy of the performance.xls spreadsheet. All right? It's got instructions, it's got infinite queue, and it's got finite queue. Okay? Infinite queue means that we don't have, think of it like a department store. You have all these people walking around the mall. Any number of them can come get in line, and there's no restriction on how many people can get in line. Okay? Think of the finite queue as something like you've got, you're working a call center, and you have only 5 lines that people can call into, right? That means if you have one server, you can only have 4 people on hold, and so therefore you have a finite amount of people that you can serve, okay? And so that's the first question when you read the problem. You need to ask yourself, am I talking about an infinite queue or a finite queue? And you have to read the problem because it will tell you in the problem, by reading the problem, that, okay, no, it can have any number of people can get in line, or it's going to tell you specifically, okay, there's only 5 telephone lines, so that's going to be your queue that you've got a finite, you're working with a finite system. Then as you're working with that, right, this is the information that you have to be able to read out of the problem. You have to be able to understand how many servers you're dealing with. You have to be able to calculate the arrival rate, and you have to be able to include the service rate of each server. Okay, so you note that that says of each server. We're not talking about, because this is going to automatically calculate it based on the number of servers that you put in. Okay, so it's the processing rate, the service rate of each server. Okay, then when we input those 3 pieces of information, it gives us the detail to come out of it. It says, on average, I sub I represents what part of the inventory? If I'm in the bank, who is that inventory?
People waiting in line.
The people waiting in line, right? And then it's how long are they going to have to wait in line, right? And then if I come down here, it gives me my average utilization at 83.33%, right? And it tells me then in total, the average number in the entire system, right? This is just I. It's not I sub I or I sub P. Is 7.938. And the average time in the total system is 0.3969. So the other thing that you have to be consistent with is that when you enter information into these cells, they have to be in the same unit of measure. So you have to be talking about in minutes or in hours, but you have to be in that same unit of measure. Okay? All right. So that being said, what I have done in this example 8.6 is I've just taken, when we input into the performance.xls, and just copied that screen into here so that we can see that information in here, okay? And so what you can see is that in example 8.6, all right, we've said that our arrival rate, right, is 10. So because it says, recall that the average passenger arrival rate is 10 customers per minute, okay, and the average processing rate is 5 seconds, okay? So because my processing rate is, my T sub P is 5 seconds, right, if I want to get my, that service rate of each server, I have to take 1 over every 5 seconds, okay? But again, here I'm talking about minutes, right? So I have to convert that to minutes as well. So it's going to be the 1 over every 5 seconds times 60 seconds per minute. 60 divided by 5 gives me 12. Okay? All right. And again, that's all spelled out for you in that example in the textbook. With one scanner, the number of servers is C is equal to 1. Okay? So that's what we've got here. We've input our inflow rate, and we've input our processing rate. Okay? And then it says, if we add another X-ray machine, right, what happens to that then? All right, so here's my utilization with 1, right? You see where the utilization comes from? The 83.33%, right? My inventory of people in line is given to me right here, right? The average time that people are in line is given to me right here, right? The average time of people in the system is right here, right? And the average number of inventory in the system is right here. So it's reading this and understanding what each of these is telling you, okay?
Are we going to get all that information in every problem?
Yes. Sometimes it won't be perfectly spelled. Like you're going to have to figure out how to calculate the inflow rate, how to make sure that they're in the same unit of measure. That's going to be some of the pieces of the puzzle, okay? All right, so let's go back to the live copy here. And so we're going to say that we're going to change that to 2 servers, right? And my arrival rate we said was 10 customers per minute, and my processing rate is 12 customers per minute, okay? And what you can see then is, if I'm trying to do this comparison, then I do my utilization, 41.67, right? It comes from this spot on the infinite capacity spreadsheet, okay? My inventory, the amount of customers that are waiting, right, is I sub I. The amount of time, right, is T sub I. Okay? And then the average number of people in the system is given here, the total inventory, right, and the total time. All right? So now here's the question. We know that the total time and the total amount of people in the system is 1.008, right? And we know that the total people waiting in line are 0.175. Can I figure out the total number of people that are in the processing? Because what does this total consist of? Everybody in the system consists of 2 components. What are the 2 components? Bless you.
Oh, gosh.
So I'm in the bank.
It's the people in line and the people actually interacting with the teller.
There you go. So I'm in the bank and I've got people that are waiting in line, right? That's I sub I. And then I've got people that are being processed, I sub P, right? And if I sum those up, that's going to equal how many people are in the system. So in the reverse of that, if I have how many people are in the system, and I have the inventory of people that are waiting in the line, I can figure out how many people are in the processing component by taking 1.008 minus the 1.175. So this begins to be about making those relationships between inventory can be broken down into those two parts, and time can be broken down into those two parts. So again, if I know that the average time in the system is 0.1008, and I know that the average waiting time is 0.0175, I can then give the average processing time by taking the difference between those two. Okay? You're going to get, when you're using this XLS, I do not understand why it comes up, but it'll come up and say, can't push objects off the screen, and you just say, okay, no problem. And it'll come back to you. So, and you say, well, why does any of this matter, right? Well, we're kind of interested. We could just at this point say, well, we're interested in the utilization, right? Because we might have a target utilization, or we might have a target time that we want customers to not have to wait any longer than. Okay, and we can address whether or not adding another server, does that hit our target, or are we still short, right? So that's the kinds of things you can address here. Okay, but what we get interested in then is we start to get interested in, well, how can we identify this cost and say, what's the best cost? Okay, and so what we do is we can use the information that we have, and we can apply it with some cost information. All right, so 8.7 says, suppose that the call center is currently staffed by only one CSR. So that means in my copy of performance.xls, my little c is going to be equal to 1. Okay? So let's go ahead and okay. And then it says, and it takes that CSR an average of 2.5 minutes to process a call. So that means that my T sub P is 2.5 minutes. Okay. So then my processing rate for that customer is one customer every 2.5 minutes. Okay, which is 0.4 customers per minute, right? In this example, we're going to go ahead and convert to an hourly processing rate. So I'm going to take my 0.4 customers per minute times 60 minutes per hour, gives me 24 customers per hour is my processing rate. I need my arrival rate, right? Because if we look at that copy of performance.xls, I need to have the number of servers, I need to have my processing rate, which we just said was 24, and I need to have my arrival rate. Okay, and it says customer calls arrive at an average of 3-minute intervals, so that's one customer every 3 minutes, right? Gives me 0.333 customers per minute. Again, convert that to hourly. 0.333 customers per minute times 60 minutes per hour gives me 20 customers per hour. So I'm going to go 20 customers per hour. All right, and right away, then I can tell that I have 4.2 customers waiting in line, right? They have an average waiting time of 0.21. Am I in minutes or hours right now? You remember?
Hours.
Right, we converted to hours. So that's saying that my customers are going to wait for 0.21 of an hour, okay? They are utilized at an 83.33% rate. There are an average of 5 customers in the total system, and it takes, on average, a quarter of an hour for them to finish the entire process. Okay, so let's go back then. And so at one customer, I'm going to try to shrink this down so we can look at it at the same time. So, at one server, right, she says as though she can get it to do this. So at one server, right, the amount of inventory waiting is what?
4.2.
4.167. Okay. And so then what I can do is I can calculate, in the problem it tells me that each server costs $20 per hour, which is another reason why I wanted to convert this to hours, because my rate is in hourly rate, right? And so basically then, if I've got one server times $20, the cost of actually having somebody performing the service is $20, right? And I can also calculate how long I can say, well, based on experience, I know that it costs $120 for each hour that someone's on hold, right? And so if that's the case, then if I have 4 customers in the system, or 4.167 customers in the system, I can multiply them by that hourly rate of $120 an hour, and I know that in effect I'm losing that goodwill, right, of $500 at that rate, okay? And so what I can do is I can kind of continue to work through this and look at, well, what if I have 2 servers? What if I have 3 servers? What if I have 4 servers? At some point, the cost of hiring more servers, right, is going to be more than the cost of the lost goodwill if I hired those servers. So what we do is we come back to our copy of performance.xls, right? We come up here and we say, well, if I have 2 servers, now I only have 0.17507 people in the system, or excuse me, people that are waiting. Okay, so 2 servers times $20 an hour gives me $40 for the cost of service, right? And my goodwill costs go down from $500 to $21, right? So clearly at this point, we're still in a winning situation. By hiring an additional server, I'm going to save that goodwill cost, okay? Then I come back to copy of performance.xls and I say, well, what if I have 3 servers? Okay, now I only have 0.0222 people that are waiting for service. Okay, and at that point, right, I have just now passed the point, it now costs me more to have the server than it does to what I'm going to gain in the goodwill. Okay, so I don't, basically, it's $20 cost to add a server per hour, and I'm not picking up quite $20 an hour, right? Just something slightly different than that. And if I go to 4 servers, right, we're going to see clearly that's going to be more expensive yet. And so I have 0.0029. And so my servers, it's 4 times 20 plus $120 an hour times the 0.0029 people that are actually waiting, right? And so my hourly cost is 80.35. So we'd come back to that and we would say, well, clearly here at 2 servers, that's the most cost effective for where we're at. Okay? All right. Let's take a look at example. And you have to pay a little bit of attention because sometimes they're going to talk to you about the inventory of people waiting, and they're going to apply their cost to the inventory of people waiting, and sometimes they're going to apply that cost to all of the inventory in the system. Okay? And so, think of every company measures things differently. So maybe they measure based on this lost goodwill, based on how long somebody's got to be in the total process. Well, if that's the case, you have to come back to the copy of performance.xls, and rather than taking this inventory number, what inventory number would I be taking? If I no longer am saying it's just how long people wait, but how long, or how many, it's not how many people are waiting, but how many people are in the total process. Where am I going to get that information?
Is it the
It's
average
the
number in the
average
system?
the I.
Right.
The 8.
It's right here, right? So this I represents everybody in the entire system. That I represents only the average inventory that are waiting for service, okay? So if they ask for that, then I have to come back through and go, okay, well, at 1, right, I have 5 people in the system. At 2, I have 1.08, and then we would just plug in, instead of this, it would be, right? And we would just continue to change that for total people in the system, Okay, so you just have to revise it. So you have to pay attention to what, when they're telling you how they're identifying their goodwill costs. Okay? All right, in example 8.8, we're going to take a look at LL Bean's call center, and it's currently staffed by one CSR who takes an average of 2.5 minutes to handle a call, and suppose that calls come in at an average rate of 20 per hour. So it's telling me that I have, from the problem, that we have 5 telephone lines and 1 server. Okay, so am I now working in an infinite or a finite system? Finite, because I now only have these 5 telephone lines available. Okay, and that changes how we do our inputs a little bit. Okay, so I go to finite. Now I have 4 things that I have to input. I have to input how many servers, right? We said that we had 1 server, right? And I have to input K, and K represents your queue capacity. So if I have 5 lines available and 1 of them is being processed, what's my queue capacity? 4. Right? So basically you're taking how many lines you have available and subtracting how many servers. So in this case I'm going to put 4, right? And we calculated our arrival rate in the previous example, so I'm not going to walk through that again, and our processing rate in the previous example, so we said it was 24. Okay? So now we get, again, the information, the average rate joining the system, okay, and the average rate leaving the system without service, meaning that because of variability in the process, these people are not going to be served, okay, or because the system is full. So again, kind of the cool thing about performance.xls is it has, using that exponential distribution, it's able to calculate the probability that if you only have 5 lines, how often is somebody, and how long it takes you to process, how often is somebody going to be able to bump up against that and not be able to get a call through, right? And so what we're saying is that 10% of the time, the system is going to be full, okay? So even though we have an average inter-arrival rate of 20, right, 10% of those people are never even going to get into the system because they're trying and the system's going to be full, okay? And then again, it tells us, okay, what's our average number waiting in line, and what's the average time that they wait, what's the average utilization of the servers, okay, and what's the average, again, of the number being served, so that's a new on this one, and what's our average number in the system in total, and the average time in total, okay? So, again, just by understanding and inputting these things, I can come back with this data. So, while this is interesting, it doesn't really become practical until we apply, what does that mean in terms of cost, right? And so we have to then translate this into, well, what are the costs of service, right? And so far we've talked about the cost of the servers themselves and the cost of lost goodwill, right? If they have to wait too long. Now we're going to need to add to that the cost of people not even getting into the system, right? There's a cost associated with that, okay? So, again, this example spreadsheet is out there, and one of the reasons I did it is because I want you to be able to see, I've kind of color-coded. So what I'm saying here is how many telephone lines? Well, if we have 5 telephone lines and 1 server, right, our buffer capacity is the number of lines minus the number of servers, right? And so then I am going to use this data, right, the probability that a call is being blocked, 10.07%. The throughput in terms of units per hour, right, comes from here. That's going to be actually how many people are able to join the system. It's no longer our inter-arrival rate because some of those people aren't going to get in. Okay, so we have to adjust that and say we're not even going to see some of those people. And then it says how many people on average are waiting, right, which comes from I sub I, right, and how many average wait time in line. Okay, and that's the T sub I, which is here, and then our capacity utilization, which comes from here. Okay, so again, it's about understanding the information that we're getting here and translating it into a table so that we can then use the table to calculate what if we compared these different costs. Okay. And so all we've done then in terms of, as we moved across here, we continued to have one server, right? But I changed the amount of telephone lines that we had. Okay, well, what if we went from 5 lines to 6 lines to 7 lines to 8 lines to 9 lines? Here's how those measures are affected. Again, interesting, but it becomes useful when you apply cost to it. Okay, so in example 8-9, we apply cost to it. All right, so in 8-9, basically we say we start with one server and 5 telephone lines available. Okay, all of this is very similar to what we've been calculating, right? Our buffer capacity is the number of telephone lines minus the number of servers. Okay, and our arrival rate, again, we calculated it in 8-7, was 20 per hour and 24 per hour. Okay, so we take this information, right, that we got in 8-8, and we apply our cost to it. Okay, so if I have one server, that costs me $20 per hour. And in this example, I'm keeping one server all the way across, right? But my telephone lines cost me $5 per line per hour. Okay, so I have to say, well, here I have 5 total lines, so 5 times 5 is 25, right? Here I have 6, 5 times 6 is 30, and etc. Okay. Then I have to say, what's my margin loss due to calls being blocked? Okay, so this is that added component of cost that we're talking about. And to calculate that, we say, well, we're going to take, it's not quite this sequence in the formula, but this is what we're doing. We're taking how many customers are trying to enter the system, our R sub I, okay, which is our 20 customers per hour. But 10.07% of them are not getting in, right? So that's how many are going to be blocked. And I'm going to multiply that times the cost of a blocked call, which is $100. Okay? So in this first one then, it's 201.40. And the second one, right, it's still 20 customers are trying to enter the system, but I've added an extra phone line, right? So only 7.74% of them are going to be blocked. So it's the 20 times the 7.74 times the $100 per hour, or $100 per blocked call. Okay? But if you can think about it, you kind of have this trade-off, right? There's a cost of somebody being blocked that can't even get into the system, and then there's a cost if they get into the system and they have to wait for a long period of time. So we need to calculate the cost of waiting time. Okay? And so basically, we're saying, you know, we knew from that last one that it was $120 per hour, and we're going to take that times the average number of people that are waiting. Okay? So 1.23 times 100, 147.6. And as I increase the number of servers, as I increase the number of lines, right, what happens is the number of people waiting actually increases, because I still only have one person serving them. But the number of people that are waiting continues to increase. So this cost of waiting per hour is going to increase over time. Okay? At some point, right, it's actually less expensive for them to be blocked, right, $121.20 if they're blocked from the system, versus $214.80 if they get into the system and have to wait for a long period of time, right? So there's, again, we've got these trade-offs. And so what we're going to try to do is assess, well, where's the sweet spot, right? Well, it looks to me like if we sum up those total costs, right, with 5 lines, our total cost is $394 per hour. With 6 lines, it's $387 per hour. And with 7 lines, it goes up to $391. So we would say $387, right? And so we would go with 6 telephone lines as the ideal. Okay? So in this example, we only varied, right? We only varied the number of telephone lines. Okay? But you could also do kind of this duality of, well, what if we vary the number of telephone lines and the number of servers at the same time? Okay? Scotty?
How do you find the K again?
So K is what we call the buffer. And so when we say N minus C, N is the total number of lines minus the number of servers.
Okay.
So if I have 5 lines in one server, 1 line isn't available for buffer because they're being served. If I have 5 lines in 2 servers, right, there's only 3 lines available for people to be waiting on. Okay? All right. And so the last example then says, well, what if we varied both of those? Okay? So what if we varied both how many people are waiting and how many people we have serving and what the buffer capacity is, right? So we looked at the effect of buffer and processing capacity on the blocking probability. So this is the blocking probability given one server and 1 buffer, right? 2 servers, 1 buffer, 3 servers, 1 buffer. What's the probability that they're going to be blocked from the system? This is the effect of the buffer and processing capacity on the waiting line with 1 server and 1 buffer, right? It's 0.27, okay? So the more servers I add, the less time they have to wait. However, the more lines I add, the more time they have to wait, right? And so then you get some kind of fun formulas in Excel, which, of course, again, you may not all think that. But basically, then you're calculating the cost of the probability of being blocked and the probability of and the cost of the waiting time. Okay. So here's how it works. So to determine the effect of buffer and processing capacity on the total hourly cost, right? We know that our CSRs cost $20 an hour, right? So I'm going to take the number of CSRs times $20. I'm going to take the number of lines times 5, right? And I'm going to get the cost of lost sales, I'm going to take the arrival rate times the probability that they're blocked times the cost of lost sales, and again the cost of waiting time. We're going to take it's $120 per hour times the customers that are waiting. Okay, and so if we look at this first example, just right in that cell. So our cost is $611.80, and it comes from doing these 4 things, right? So I say, how many servers do I have? Well, I have 1 server times $20, right? Trying to make sure. So I have 1 server times the $20, okay? Then in the next one, I take H24, and H24 is the cost of the line charges times the number of telephone lines, okay? And then I'm going to take the, for the cost of lost sales, I'm going to take the arrival rate of 20 per hour, right, times the probability of being blocked, 27.47, times the $120 per hour, okay, and times the $100 per hour. And for the cost of waiting, right, it comes from this table, the 0.27 times $100 per hour, right, because that's the number of people that are waiting. So this is just a combination of what we did in these 2, right? It's just saying, we're not saying you can only vary the number of servers. We're not saying you can only vary the number of lines, but that you can vary both, okay? And I don't think, let's take a quick peek at your homework. I don't think that we do anything quite that complicated in your homework. Yeah, so we start off with 1, and basically I just want you to tell me what these values should be, because I want to make sure that you understand how to get those values before you go through the whole problem and you can't get those values. Okay, so then you can check your answer against what's posted, right? Then you move on to 8B2, and 8B2 says, okay, now that you've got that information, use performance.xls and tell me what's the server utilization, what's the average waiting time, what's the average number of customers on hold, and what's the average number of customers in the system. So it's just getting used to reading the information on that performance.xls. Okay, and then in 8.3, from the work that you did in 8B1 and 8B2, now we're going to talk about hourly cost. Okay, and so now we're saying if what's the hourly cost of service and waiting? So you're only looking at two components in this one. So service is going to be, again, how many servers you've got times the cost per hour, right? And then your waiting, right? You're going to take the amount of people that are waiting and multiply it times that cost. All right. So again, the 8B is kind of more of the simple, okay? Then I'm giving you another problem, and then the question, should you use infinite or finite? What's the value of K? And then you're going to plug stuff in, and then you can check your answers against this. So again, it's just about inputting information into performance.xls and answering the questions. And then in the next one then, that's when you're going to calculate, okay, what's the cost of providing service? What's the cost of waiting? What's that hourly loss because customers can't get through, so the probability of being blocked? And what's the total cost of the service? And so then this is just a conceptual, you can put it into the spreadsheet and do it from there. But that's what we're looking at there. Okay? And then in 8C, we're going to do the calculations like what we looked at towards the end of class. So let me go ahead and bring that up real quick. Oh, so it's 8.12. Yeah. And then I think 8.11. So I'm asking you to do two problems out of the back of the text. All right? So I have a couple of quick kind of conceptual questions for you just to kind of make sure that you're leaning in the right direction here. Okay? So make whatever notes you need to as I talk about this, but here's the question for you. So a call center has 12 telephone lines coming into its customer service department. Okay? And it has 5 customer service representatives. Okay? On average, 2 potential customers call every minute. Each customer service representative requires, on average, 2 minutes to serve a caller. Okay, after great deliberation, management has decided to add another line, increasing the total lines to 13. Okay, so if I increase my number of telephone lines, will the proportion of potential customers getting a busy signal increase, decrease, or be unchanged? If I add another phone line, will the customers trying to call in getting a busy signal, will that increase the number that get a busy signal, decrease the number that get a busy signal, or be unchanged?
Okay.
Okay. Everybody agree?
They didn't add another rep.
Okay.
Wouldn't it decrease?
It's going to increase the number that get a busy signal.
It's going to decrease the number that get a busy signal.
Wow.
So if I have 5 telephone lines today and 1 customer serving it, I have 4 lines available for people to be on hold. If I add another line, right, that's going to decrease the number of people that get a busy signal because when they call in, this guy is still serving at the same speed, but now I've got another line for them to wait on, for them to populate when they call in. So the number of people getting a busy signal is going to decrease.
Oh,
Okay.
so
Okay.
they're just going to be on hold. I mean, they're
Right.
still not getting served. There's no more service.
There's no more service, but I want to walk through these questions because I want to make sure you're compartmentalizing right. Okay. So the next one is the average flow time experienced by customers. So now that I've got the one being served and I've got one more on hold. So the average flow time is it going to increase, decrease, or remain unchanged? So here's let's see. So here's my 6 lines, and so I started out, I had 5 lines, and I had 1 person on hold, and then these 4 people were going to process through and get to this one. Now I've got a 5th person. Is it going to take him longer to get to being processed, or is it going to remain the same, or is it going to be faster? Not sure?
Would it increase?
It does increase, yep, because now instead of 4 positions to wait through, I now have 5 positions to wait through to get served. Okay? So the average flow time is now going to be longer because it takes me longer to get through those openings to be served. Okay? What about average utilization of the customer service representative? So here's my customer service representative, and I had 4 lines that I could, or I had 5 total lines that could be served. Now I have basically 6 total lines, and I'm serving 1 of them. Am I going to be more utilized, less utilized, or it remains unchanged?
More.
Say that again?
More.
You're correct, right? Because that variability, I can get that last customer that's calling in, whereas before I wouldn't get that customer. Okay, they would just be blocked from the system. Okay? Let's do one other example like that. A mail order company has 1 department for taking customer orders and another for handling complaints. Currently, each department has a separate telephone number. So I've got 2 departments with 2 different phone numbers. Each has 7 telephone lines served by 2 customer representatives. Calls come into each department at a rate of 1 per minute. Okay. Each representative takes about 1.5 minutes to serve a customer. So management has proposed merging the 2 departments and cross-training all the workers. So now we would have 14 telephone lines served by 4 customer service representatives. Okay. So if I have 14, so I still have the same number of telephone lines, but I've combined up those 2 departments. So is the proportion of callers getting a busy signal going to increase, decrease, or be unchanged? So I went from 7 lines over here to 7 lines over here to 14 lines in total. So the callers getting a busy signal, does it increase, decrease, or remain unchanged?
Unchanged.
Okay. You think unchanged because we're combining them up and we still have the number of servers. Okay. And everybody agree with that?
Would it increase?
And why do you think it would increase? So I've got
Just
7 and
because
7.
you're adding them.
So now I've got 14 total lines. Okay. So this is related to how variability works. Okay. Because if I only have 7 lines over here, right, there are going to be times when I can't get in on these 7 lines, and there's going to be times when I can't get in on these 7 lines. If I combine them up, those times you're averaging out that variability. And so they're actually going to get less busy signals because that variability where you have it segregated here by the 2 groups, now you combine it and you average out that variability and it makes for less change. Okay? So that's why when you combine up like that and you cross-train, you actually get less waiting time. Does that make sense, or do I need to say it another way with another example? Rachel, does that make sense?
I think so.
Okay. All right, Spencer? Okay. Andrew? All right. Because basically, that's a fundamental thing that you should take away from statistics, is that when you can average out variability, right, then that means that you're reducing that variability, that the impact of that variability. Okay? And an average flow time experienced by customers will it increase, decrease, or be unchanged? Kaylin?
Decrease.
It's going to decrease. And why is it going to decrease?
Just because you have all those more lines now together. Well, the cross-training, wouldn't it?
Yes. So it's the cross-training, not the more lines. Because the more lines, if it were just about more lines, that would actually increase the amount of waiting time. But the fact of the matter is we're taking that variability and we're, again, combining it. And so we're saying that we're reducing the amount of variability in terms of processing times, too. We're putting that together across both departments. Okay? So those are kind of 2 different ways. You might want to review those in your textbook. Those are 8.1 and 8.2 questions in your textbook, and because they're kind of 2 different ways to look at, well, what happens when we make changes. One of them is if you're only talking about 1 department, right, and you add more lines, that increases the waiting time. But if you're talking about 2 departments and you don't change the number of lines and you combine them and do cross-training, that's going to decrease the overall wait time that people have. Okay? So that's the extent of what I've got for you today. I'll be in my office on Tuesday, so if you have questions about your project or you want to make an appointment with me outside of that, make sure you make good contact. And other than that, I'll see you back here the following Tuesday with the expectation that you're going to have a presentation to give to the class on your project.
When are these going to be unlocked? Your homework assignment.
We're already.
No,
They say they're locked.
she says. I'll go up and yeah, I'll just do them. Because I think I've got Canvas.
Yeah, it seems they were locked yesterday.
Yeah, the one that.
I don't understand a lot of what she got up there was different than what we.
Wait.